Right, moving on to question 2. We have a car, mass 1,400 kilograms. It's moving along a straight horizontal road against a resistance of magnitude 350 newtons. Find in kilowatts the rate at which the engine of the car is working when it is traveling at a constant speed of 20 meters per second. So, we are being asked to calculate power, because power is measured in watts, and we will obviously then convert to kilowatts. We have resistance, and not only that, we are told that the car is traveling at a constant speed, right? Now that's important. When we are thinking about a constant speed, that means we have constant velocity, and when we have constant velocity, there's no acceleration, and that means that the forces are in equilibrium, which is great because then we can calculate the forces acting on the car. So let's just draw a simple diagram for ourselves. We're just going to draw a horizontal surface, and we can draw the motor vehicle. And let's consider the forces acting on the car. The first thing we're going to do is we're going to set the direction of motion. So we can say, let's say that's the direction of motion. Now the reason we need to set direction of motion is because resistance always acts in the opposite direction. So if we're traveling in this direction, that means my resistance forces must be acting in the opposite direction, and they tell us these are 350 newtons. That could be friction, air resistance, it doesn't matter, but that's the total resistance. Okay, if the car is moving forward and is in equilibrium, that must mean there must be some driving force pulling the car in that direction. And while we can consider, but not important, is the weight of the car and the contact force, and the reason they're not important is because they're perpendicular to the direction of motion. Okay, if this car was moving up a hill, we might have to consider these, but since we're on a straight horizontal road and they're perpendicular, they have no effect on the work being done by the car. Right, since the forces are in equilibrium, right, we can even say since velocity is constant, we can say that the forces are in equilibrium, and that means the forces acting in one direction must be equal to the forces acting in the opposite direction. And the only force we have acting in the direction of motion is the driving force, and the force acting in the opposite direction is the friction force. Right? If they're in equilibrium, that must mean they are equal to 0, and therefore we can solve for the driving force as 350 newtons. Now that we have the driving force, we're able to calculate the power of the car. Okay, now remember, power is equal to force, and this force here is not net force. This is the driving force. Okay, it's not like Newton's second law, force equal to mass acceleration. That's net force. This force here is specifically the driving force, the force itself that we're considering for power, times velocity. Okay, instantaneous power, since it's change in displacement over change in time, and the instant of, well, velocity in this case is 20 meters per second. So we have a driving force of 350, a velocity of 20, and that's going to give us 7,000 watts. Okay, now we were asked to calculate kilowatts. Kilowatts is just 1,000, so 1 kilowatt equals 1,000 watts. And so our answer would be 7 kilowatts. Okay, part B says find the acceleration of the car when its speed is 20 meters per second and the engine is working at 15 kilowatts. So we're going to use what we've got and we're just going to work backwards. Okay, so now we have some other forces acting on the car. The forces are no longer in equilibrium. right? So we can't say the driving force is equal to the resistant forces. We're going to work backwards to calculate the driving force, and then using that we can solve for the acceleration of the car. So this is how we'll do it. Okay, once again, power is equal to force times velocity. And this time we've been given the power. We're told the power is 15 kilowatts. Okay, we want to calculate the driving force, and we know the velocity of the car because they give it to us as 20 meters per second. Right, this means we can calculate our driving force. So remember, it's 15,000 watts divided by 20, and that's going to give us 750 newtons. That's the driving force of the vehicle. Okay, so if we have a look at our original diagram, we can actually change. So we'll just copy this quickly. So here's our diagram again. Direction of motion is still the same. Resistance to motion is the same, except this time we've calculated the driving force as 750 newtons. Okay, now again, this is a straight horizontal road, so the weight and the contact force don't make a difference in our equations. So if we have a look at the diagram, we can see the forces acting in the direction of motion are greater than the forces acting against, right? And therefore the forces are not in equilibrium, and there must be acceleration. Okay, so now using Newton's second law, force equals mass times acceleration. This is the net force. Okay, so where we take the forces in the direction of motion and we subtract the forces in the opposite direction to get the net force. So we've calculated the driving force is going in the direction of motion. The resistance is 350 newtons. There's our net force. And this must be equal to mass times the acceleration. Acceleration is what we're trying to find. We have to go back to the beginning and see the weight of the car given to us was 1,400 kilograms. So remember, the mass is in kilograms, so we're not converting this to newtons. Okay, we're not looking at force times acceleration, it's mass times acceleration. And A is what we're trying to solve for. So we just simply take 750 minus 350, and we divide that by 1,400, and that's going to give us an acceleration of 2/7, okay, which we can write as 0.285714. We'll write a few numbers, and we need to remember 3 significant places. So 3 significant places means I need to round to the 5, so I need to consider the 7. The 7 is greater than 5, and so we can get 0.286 meters per second squared is my acceleration.